So this is shown here, but we have some sort of infrastructure around information retrieval. We do have the query language, the but not, and the and. We do represent documents and queries in canonical form, and we do have a ranking function. And then we have some sort of mechanism to feed back information from the user based on either, usually implicitly, because what the user chooses will tell you whether you did a good job in your search engine. Here's a very important point, which is true in many of these optimization problems. So suppose we have a query, and this purple egg is all the results that in a perfect search engine would give. But now our search engine comes along and gives the green egg. So we have A, the purple egg, relevant documents, B, the actual retrieved documents, and then we have two important numbers. One is recall, which is this area here, A intersect B, divided by A. That's the fraction of relevant documents that are actually found. Another important number is the precision, which is the same area, but now divided by the size of B, which is the fraction of returned objects which actually have any relevance. So one is the fraction of relevant documents found, the other is the fraction of retrieved documents that are relevant. So you can obviously trade these off against each other. If you have an algorithm might get all the relevant documents, but give you so much noise as to be irrelevant. So if the egg here was so big, well, you could return everything. Then the egg would be the whole world. That would have a recall which was 100% perfect, but the precision would be terrible. So, and of course, an important point which we'll be mentioning a little more later on is that there's no such thing as an exact relevance of a document is not either relevant or irrelevant. It typically has a probability of being relevant, and most modern systems are built around such fuzzy or probabilistic models. So what points out here, precision is the dominated factor. Namely, remember what precision was? Precision is the number, this thing here, over this thing here. So precision is that most of the results returned are high quality. So users tend to be satisfied with having not too much junk in the response, and they're willing to accept losing some important return documents to actually get high precision. So that's true for broad topics which probably have so many good responses that there is no chance of getting a good recall. If you do a narrow topic query and you're only looking for a single document that will satisfy it, then you have to really have a very different optimization to get a very good recall, because unless you get a good recall, you might not find any answers of relevance. So the measure that's typically often used is position at 10, which is looking at the top 10 documents and seeing how many of them are actually relevant. Remember, position is the number of elements over the total. Here, the total is by definition 10, and we want to know how many of those are relevant. So remember, we're also ranking them, so those are the top 10 ranked documents. As we noted before, diversity has some value. Here's a comment from Google in September 2012. It says, Google just changed its search engine to improve diversity. And an example of what was wrong was a particular query about Christopher Jackman plates only gave answers, at least all the top answers from Christopher Jackman's website, and that was not very diverse. So Google tweaked in a way that they don't tell you what they did to improve that. And obviously, it probably wasn't a very big change, and so it's a small algorithm change. So we've already pointed out in many fields that it's very important to have spaces. In the recommender systems, we have user spaces, content spaces, and item spaces. And by looking at the things we were considering in those different spaces, users in the space of items, items either in the space of user or in the space of content, you were able to think of these things as points, think of the points as being near each other, and that was sort of the fundamental formulation of your problem. In the case of information retrieval, the space is not the space of, it's a space of words. It's sometimes called a bag of words because you do not look at the ordering of the words in this simple representation. And you look at all possible words, that's your vocabulary. Of course, you can find that by just scanning the documents. And you then just count how many times a given word occurs in the document. And now this is a case where you have a real vector space, and that every document does have an actual number of times each word occurs. Probably lots of them are 0, but it's not like say collaborative filtering, where a given item in the space of users just is undefined for some users because it's only defined, its ranking is only defined for the users that have ranked it. The ranking is not 0 for the other users, it's just undefined because the user has not ranked it. And those users which have not ranked it, many of them could rank it very highly. So, documents are represented by the terms. The terms, of course, are just cleaned up words, and documents are represented by the words it contained. And if we take our standard phrase, that's one small step for man, a giant leap for mankind, you see that occurs once, one occurs once, small step occurs once, 4 occurs twice, a occurs twice, man, giant leap, and mankind all occur once. So that's the vector. Of course, you typically don't use the words like a in any search engine. You remove such things. So if you take the simple bag of words model, you lose the word order. You could have documents which meant very different things, having similar representations. Things like headers, and in the case of, say, scientific documents, you have title, abstract, authors, citations, main body of work. They're all very different. That type of thing gets lost unless you deliberately remember the structure of the document. It's a very simple method. That's why we tend to like these vector space models. They provide a very elegant, simple approach. It's relatively intuitive what you're doing. This also tends to be implementable quite efficiently, and it also works quite well. Bag of words is a good idea. So any documents represented by a vector, and so here is the vocabulary. Those are the components, and those labeled the dimensions of this vector. We have 14 possible dimensions, and here is a couple of sentences, and they're just mapped into particular vectors, so-called incidence vectors. So it says here that occurs once in this sentence and 0 times in that sentence. Size occurs 0 times, of course, in this sentence and once in that sentence. 4 and a occur twice in this sentence. Nothing occurs twice in this sentence here.